Thank you, Barbara, for organizing this. I guess it's the first in-person workshop I end up attending since this whole thing started. And for the last 2 years, we've been sending titles, and I kept sending the same title. And yesterday, I was like, whoops, what am I going to say? So I'm going to be speaking about phase transitions in the Earth's mantle and effect on the microstructures, and how you can observe it seismically and the link with seismic observables. Just to mention, we have actually quite a big project between the University of Münster, GFZ in Potsdam, the University of Lille, where that is dedicated to look at phase transformation microstructures and the effect of seismic observations. So you have the PIs over here and students and postdoc participating in the project. And so there will be 2 posters later tonight, one on what's layout in the transition zone, and a second poster on what's happening below the 660 discontinuity. And in my talk, I'll focus a little bit more about D double prime. So phase transformations, I guess most of you know this figure. That's phase transformations in a paralytic compositions, and you can relate phase transformations to discontinuities in the mantle. It tells us an idea on the dynamics, composition, history of the mantle. And how do you observe phase transformations through what is the connection between phase transformations and seismic observations? Well, phase transformations creates very sharp changes in physical properties, so you get those seismic reflectors, and you can locate boundaries within the Earth. You get wave conversion. So it's a very clear region in the Earth that they can map with seismic observations. But they also have a microstructural effect. Like, for instance, you can have very aligned grains above a discontinuity. Then you get a phase transformation and everything becomes random. In this case, you'll have anisotropy. In this case, no anisotropy. So phase transformation will also affect anisotropy observations. And then you can also do, Tina Thomas will probably speak about it tomorrow, a complex measurement of polarities, of reflections, and I will also tell you something about anisotropy. So how about detectability? Why do you see phase transformations and why don't you see phase transformations? For instance, here's a map from a synthesis of Laura Cobden, where are reflections that you can see on top of D double prime. So if you think there is a transition between Bridgmanite and post-perovskite in D double prime, you might expect to see reflections in quite a lot of locations on the Earth, but actually you don't. I mean, sometimes you do. You see a lot of regions where you see S reflections. You see P reflections in some parts of the D double prime layer, but not everywhere. And so the first, but then using other approaches, and people in this room like Paula Kollemeyer have looked at it as well, you can infer presence of another phase like post-perovskite in D double prime through tomographic model by mapping changes in velocities in your tomographic model to physical properties. You can even map the height at which you expect the phase transitions based on those models. So seismic observations tend to tell us there is something happening, there is a phase transformation. And then why don't you see it always? From a mineral physics point of view, the first, actually you don't see the gray here, so one of the first questions is, do you actually have post-perovskite in the lower mantle? This is the limit in pressure between the mantle and the core. And those papers from 10 years ago or so argued that depending on the composition, you can go from perovskite to post-perovskite structure, sure, but sometimes the pressure at which the transformation occurs is too high, and so it would not happen in the mantle for a pyrolytic composition, and it will happen for a morph composition. On top of that, the coexistence layer, so the thickness of the coexistence layer between Bridgmanite and post-perovskite can be quite thick, like 100 kilometers for morb or more for pyrolytic composition. So maybe that's why you don't see it so well. We looked at it from another approach, which I was wondering, like, how fast does it take to go from perovskite to post-perovskite? Those experiments are never done like that. You don't go from perovskite to post-perovskite. You start from a glass, you heat, and you see where you land. It's really difficult to go back and forth. So we actually did to try to take a perovskite, go in post-perovskite stability fields, and measure how long it takes. So those are somewhat simple measurement at a synchrotron, except you just have to wait for sometimes a long time. And you have to, if you don't know the conditions, you're in the void. Sometimes nothing happens, sometimes things happen. And you have limited time at your synchrotron. But here are kinetics measurement of phase transformations between Bridgmanite and post-perovskite at, this is 130 GPa. And you can see peaks of post-perovskite growing, and you can see Bridgmanite here that is disappearing. So based on this type of data, you can actually fit the kinetics of the transformation. So how long does it take to convert Bridgmanite into post-perovskite? So there's a very strong effect of temperature. It's an Arrhenius process, so you have measurement here at 1600K, 1700K, 1800K. We did it for several pressures as well. And based on this measurements, we built a model of kinetics of phase transformation from Bridgmanite to post-perovskite. This model, so what is plotted here in the color scale is the time scale of the transformation, the time scale in this exponential law here. And, and this is a typical geotherm, this is pressure, this is temperature. So based on the experimental data, for instance, if you have a cold geotherm and you heat the perovskite to post-perovskite boundary here, it will take you around 10,000 seconds, so around 3 hours to go from perovskite to post-perovskite. If you are on a warmer geotherm around here, you will heat the transformation between Bridgmanite and post-perovskite, then it will take you on the order of 100 seconds. And if it's warmer, it can be even faster, 1 second or less. So it's very sensitive to temperature. It's also sensitive to pressure. Now, this is based on experimental results. In a diamond cell, our grain size is on the order of a micron. In the Earth, I don't know, but probably bigger. Now, it depends on the transformation model. If your transformation is controlled by a shear transformation model, if you just have shuffling of layers in the crystal structure, this will not be very dependent on grain size. If your transformation is more nucleation of a high pressure phase that is growing over time, then it will be proportional to grain size. So this is highlighted here. If your time scale is proportional to grain size, if you have a millimeter grain size in the metal, you just have to multiply all the numbers by 1,000. It's a very rough model, but it's all we can do based on our data. Now, where is the link with the detectability? Well, what happens is when you are on the order of 1 second, 10 seconds, 100 seconds, those are the timescales of seismic waves. The periods of seismic waves are on the order of 10 seconds. And so you could expect that there is an interplay. Harky kind of alluded to it in his presentation. There is an interplay between seismic velocity, seismic waves, and the phase transformations. So reflection coefficient, when you go from Bridgmanite to post-perovskite, for if you assume an infinitely thin layer and a sharp transformation between one phase and the other, is 2.5% for S waves, which is quite low. If you do the calculation for P wave, so reflection coefficient for P wave between Bridgmanite and post-perovskite is 0.5%. It's even lower. Now, there was this stream of papers published by the Lyon group, where they were trying to look at the effect of phase transformation on attenuation, but they also looked at reflection coefficients at the boundary. They were looking at it at the 410 discontinuity, and it was not important. But I saw this figure. I was like, oh, we have to do the same thing. So we called them. We called Stéphanie Durand, who helped us with the calculation. Here is the dependence of this time scale. So the reflection coefficient as a function of time scale and wave period. And you can see it can go from a few percent to very high numbers. So when you apply that to Bridgmanite to post-perovskite, and it depends on the thickness of the layer. If your layer is very thin, nothing happens. If your layer is 10 kilometers thick, if you have 10 kilometers of coexisting Bridgmanite and post-perovskite, then you get an amplification effect of the reflection coefficient. So here is the wave period, reflection coefficient for S waves. And so you get an amplification, and it depends on the time scale of the kinetics for the transformation. So if you have 1 second kinetics, and your reflection coefficient can increase dramatically. If you increase the thickness of the coexistence layer, the effect still exists. It's actually even higher. So the more, the thicker region of coexistence between Bridgmanite and post-perovskite, the more reflection you may have. You can look at the details of those curves. So the reflection coefficient depends on the period, depends on the time scale of the transformation. So I spoke with several seismologists about it, and they told me, well, it's really hard to measure. So I know it's very hard to measure, but if you can, if you could measure the frequency or time and period dependence of the reflection coefficient, you should see a cutoff. And this cutoff is dependent on the thickness of the coexistence layer between Bridgmanite and post-perovskite. So there will be a way to measure a thickness of a coexistence layer between both phases. And then the amplitude of the reflection coefficient is, okay, I've lost the laser, it doesn't matter. The amplitude of the reflection coefficient depends on the kinetics of the phase transformation. So you could tell us about something about kinetics of phase transformation in the deep mantle. When did I start? C'est combien de temps là-dessus? Oui, mais j'ai encore beaucoup de choses. Ah oui. And you can do the same exercise for S-wave, and the effect is very similar. So I'm not going to walk through to the images, but there is an interplay between kinetics, wave period, and reflection coefficients. So that was my first part of the presentation. So on the detectability of phase transformations, yes, phase transformation induce very sharp changes in physical properties, but sometimes you don't see it because it's actually hard to see. The impedance contrast is small. But actually, when you look, there is an interplay between kinetics of phase transformation and reflection coefficients, and it's really relevant for D double prime. I don't think it will be so relevant for the upper mantle because it's too cold. The kinetics are too slow. But for D double prime and the deep mantle, it's important. So the next step is, as I said in the introduction, phase transitions have an effect on microstructures, and this is what we will be looking at now, so it's a different topic. You had this publication from David Dobson in 2013 where he said, well, you actually have an orientation relationships between Bridgmanite and perovskite and post-perovskite in an analog. And so when you go from perovskite to post-perovskite in the deep mantle, there will be a memory of the texture of the microstructure. And it's important because if you think of the subduction in the mantle, so imagine subduction when you go from Bridgmanite to post-perovskite. If your mechanism has orientation relationships, you will get some form of a memory of the microstructure, anisotropy, whereas if you have no orientation relationship, everything tends to be erased, and you start with a blank, clean material after the phase transformation. So we decided to test that in the bulk, not using TEM images on the resulting sample, but really looking at a bulk sample. There are different models. That I showed the model of David Dobson, but there are more, one from Tsuchiya, one from Oganov. They all share some common features, but there are some slight differences in the way you go from one phase to the other. So to do that, we use a new technique which took us many, many years to get it working, which is called multigrain crystallography. And the idea is in a diamond cell sample, you can use a single crystal, that's one way, or you can actually use a polycrystal, and then you have many grains. And instead of using the many grains as a powder, which is typically done in high-pressure experiments, we want to track the grains, all of them. I mean, I would like to track all of them, but at least 50% of them. And so there is a technique where which involves basically a tomography of diffraction, where you reconstruct the 3D features of diffraction of your sample. So you step scan the sample in front of an X-ray beam, you look at how the diffraction pattern changes with rotation, and you can reconstruct the microstructure. Typical way, so you collect, we're working with, for each pressure, we're working with 50 to 100,000 diffraction spots. Then you do million iterations in orientation space to match the spots with the grains. And with that, we can follow 500 to a few thousand grains. And then from those few thousand grains, for each one, we know the orientation and we have an idea of its volume. We don't know where it is, we know its orientation. And what is great for high pressure mineralogy is you can actually use that in a diamond cell at high pressure and high temperature. Hauke actually alluded also to the fact that it's really difficult to do experiments at both high pressure and high temperature, except for phase diagrams. And with this technique, you can actually do deformation. So this was one of the first experiments that worked, where we worked on an analog, NaCOF3, trying to go from perovskite to post-perovskite and back. So we're going to look at a sample of perovskite going to post-perovskite and then back to perovskite with this technique of multigrain crystallography. It's an analog. At the time, we didn't know how to do it at very high temperatures, so it was not possible on post-perovskite. So we're going to look at perovskite at 14 GPa before it goes into post-perovskite and then post-perovskite after the transformation. So this is the type of result you get from such a technique. So the image here at the bottom is a map representing grain orientations. You don't have to know how to read it, but it's just grain orientations. And each dot on the figure is a single grain that we are tracking. So we're tracking each of those dots to see what's happening as we increase pressure or go through phase transformations. So in this case, we are following 1,000 grains of perovskite and NaCOF3, and and this is kind of our indexing capabilities. Just one thing I forgot to mention, around the same grains, you have a powder which we cannot index, and here it's around 50% of the sample. Then you transform it to post-perovskite. The powder tends to disappear, and you get more grains, a lot more grains. We get 3,000 grains of post-perovskite. And here is a map of the orientations of those 3,000 grains. This is indexed before and after the transformation. So what is the link to the transformation mechanism? Well, at first, we wanted to be able to say, well, that grain here, that becomes this one in post-perovskite. It doesn't work. We don't have such a resolution. But we can look at the statistics of it. First of all, we are losing some of this fine matrix that was around the sample. The number of grain is multiplied by 3. Here you have a concentration of orientation on O1. You find the same concentration of orientations on O1 in post-perovskite. That's consistent with mechanisms proposed in the literature. And then you had here concentration of orientation. You find it around here and around here as well. And that right away tells you, it's consistent with what David Dobson had suggested, actually. So then you can go a little bit further and use the orientation relationships of David Dobson. So here I plugged in the orientation relationships of David from those grains and say they are transforming to post-perovskite, and this is a simulation based on this mechanism. So the simulation tells you you should have 2,000 grains, from 1,000 to 2,000, and this should be the orientations. It's kind of what the experiment, it looks a little bit like the experiment. One feature is the number of grains is different. And I kind of insisted that I was losing powder in the experiment. We were losing powder, and we think like some grains are nucleating from this powder. So we just add them. We add 900 grains that are nucleating from the powder. We add them randomly. So when I add the 9,000 randomly nucleating grains to my simulation of phase transformation, I get a figure which is actually pretty close to what we measure experimentally. It's not perfect, but most of the features are there. Now, this is when you go from perovskite to post-perovskite. What happens when you go back from post-perovskite to perovskite? So, oops, I went the wrong way. When you go back, this is the figure before, this is the figure after. One thing you notice, before we have many grains, thousands. After we have very few, and actually those very few grains have have a very consistent orientation. Maybe you don't see very well. There is a big yellow spot here. They all share a common z-axis. And then you see two strong maxima here, another one here. So it's not only it's not so many grains, but they are very close to each other in orientations. And I think there's a question of what is a grain anyway. What a grain you see in diffraction and a grain you see in electron microscopy is not the same thing. In diffraction, you see orientation space. And so I think here we see many domains very close to each other in orientation, but it's probably just one grain. Or just a few grains, not so many. So the mechanism is completely different. You decrease the number of grains. There is obviously no orientation relationships. So the mechanism when you revert from post-perovskite to perovskite is not a martensitic mechanism with orientation memory. It erases everything. So the take-home message is, based on those experiments, is when you go from perovskite to post-perovskite, you have an orientation memory. Dobson-like mechanism works. It's consistent with our data. Division of grain size by 2, because you have 2 possibilities of going from Bridgmanite to post-perovskite due to symmetry. And as you revert, actually, it's not the same mechanism. There is no orientation memory. It's more a nucleation and growth mechanism, and the grain size goes up by a significant factor. I put 10 here, but it's hard to evaluate. It goes up by a lot. So when you look at perovskite and post-perovskite in D double prime, well, you could think during a subduction, perovskite is deforming through dislocation climb, dislocation glide, or whatever. As you transform to post-perovskite, you will keep a memory of the orientation, and the grain size will be divided by 2. As you are along post-perovskite, along the core Mantle boundary, post-perovskite will be deforming, moving, and rotating through its own deformation mechanisms. But as you go into perovskite again in a hot region of the Mantle, I think you will lose everything. You will lose the history of what was happening before, and your grain size will actually go up. And then perovskite will live its life in the Mantle. Now, in terms of perspectives, what we can, this was experiment we did a few years ago. Now we've improved it by combining this technique of multigrain crystallography with laser heating. So the idea is to be able to follow a Mantle geotherm. So in terms of, here is a very simple image that I use with my students of a Mantle geotherm. Before that, this is what we were able to do in terms of deformation experiments with the diamond anvil cell. In terms of PT range, we could go to 1,000 Kelvin, maybe 100 dPa. I don't know, okay, you reach 80, and then you break everything. Cost a lot of money. With multigrain X-ray diffraction coupled with laser heating, you can actually follow a geotherm. Now, I should probably put this broader. We don't control temperature so well. Our temperature errors are plus or minus 500 degrees, but still we are on the geotherm. So for instance, I give you a primer of what's on a poster in the poster hall, where we looked at what's layout in the transition zone. And those are our results, but also results from the literature combined. But we managed to do deformation experiments of what's layout at the conditions of pressure and temperature of the transition zone with the diamond anvil cell. We identify the type of deformation mechanisms. And when you combine with data from the literature on Moise layout is really confusing. There's many experiments that are conflicting, but actually it turns out that you can plot it as a function of temperature, as a function of water content. When you are at low temperature, low water content, you get one type of deformation, one type of microstructures, and this will be the corresponding anisotropy in a simple shear deformation. When you are at high temperature, you'll get a different type of anisotropy, high water content, another one again. Anyways, there is a poster, so you can look at it. So phase transitions in the Mantle. Well, today I tried to talk to you about D double prime, detectability, and the effect of kinetics and the effect on microstructures. Then I advertise again the 2 posters, one on the transition zone and one on the Mantle below the 660. Thank you.